Welcome back to our deep dive into the Lucasian Professors.
Yes.
We're on our 14th episode.
Wow.
And today,
Yeah.
we're going to be tackling the 13th holder of this prestigious chair, Sir George Stokes.
Absolutely.
Now, you might not know his name as well as Newton's,
Right.
but Stokes' work is foundational to a huge amount of modern science and engineering.
Oh, absolutely.
So much stuff.
Yeah. His impact is immense.
And for this deep dive, we're focusing on an area that'll really resonate with your STEM-loving mind's fluid dynamics.
Yes.
Get ready to explore how Stokes' work helps us understand everything from weather patterns to blood flow.
Indeed.
It's amazing to think how the work of someone from the 19th century can still be so relevant today.
It really is.
To set the stage,
Yeah.
Stokes held the Lucasian chair for over 50 years.
That's right.
Can you imagine the sheer volume of work produced in that time?
It's mind-boggling, isn't it?
It really is.
And during those years, he made groundbreaking contributions across physics and mathematics. But one of his most enduring legacies is his work on the Navier-Stokes equations.
Ah, yes, the Navier-Stokes equations.
Yeah.
These equations are essentially the mathematical backbone of fluid mechanics.
Absolutely.
They describe how fluids move, taking into account factors like viscosity and pressure.
Exactly.
Think about it. Water, blood, they're all fluids.
Yeah.
And these equations help us predict and understand their behavior.
That's right.
But here's the catch of C's. The Navier-Stokes equations are notoriously complex.
Yeah, especially in their most general form.
Okay, so we have these incredibly important equations that describe how fluids behave.
Right.
But they're really hard to solve.
Where does Stokes fit into all of this?
Well, that's where Stokes' genius comes in.
Okay.
He made significant contributions to simplifying these equations, especially for incompressible fluids like water.
Okay.
And those simplifications have had a huge impact on how we apply these equations in real-world scenarios.
Can you give us an example of how Stokes' work simplified these equations?
Certainly.
Let's look at the convective form of the Navier-Stokes momentum equation.
Okay.
Stokes' work is woven into the very assumptions about the Cauchy stress tensor used in this form. His insights helped to streamline these complex mathematical expressions.
So Stokes made these equations more manageable.
Yes, he did.
But did he ever actually solve them completely?
That's where it gets even more interesting.
Okay.
Even with Stokes' simplifications, the Navier-Stokes equations are still not fully understood mathematically.
Wow.
Proving certain properties about their solutions is actually one of the biggest unsolved problems in mathematics.
That's incredible.
It is.
It's almost like we have this incredibly powerful tool that we don't fully know how to use.
Right.
It makes you wonder what breakthroughs are still waiting to be discovered.
It really does.
But that's the beauty of science, isn't it?
Absolutely. There's
There's always more to learn, more to explore.
That's right.
And even though we haven't cracked the code of the Navier-Stokes equations completely, Stokes' contributions have brought us closer to understanding the complex world of fluid dynamics.
They certainly have.
So we've got these complex equations that describe how fluids behave, and Stokes made them a bit easier to work with.
That's right.
But what about real-world applications?
Yeah.
Where do we actually see Stokes' work in action?
Well, let's move from the theoretical to the tangible and talk about Stokes waves.
Okay.
These are the waves we typically picture when we think of the ocean.
Okay.
Those with pointy crests and rounded troughs.
Okay, I'm picturing those classic ocean waves now.
Yeah.
How did Stokes contribute to our understanding of them?
Stokes developed a method for describing these nonlinear waves, going beyond simpler linear models. This was a major step forward because it allowed for a more accurate representation of how waves behave in the real world.
That makes sense.
Yeah.
So his work helps us understand how these waves form and move.
Exactly.
Right.
His work here helps us understand how waves behave in deep water and how they change as they approach the shore.
Okay.
Think about the implications for coastal engineering and ship design.
It's amazing to think that the shape of a ship or the design of a seawall can be influenced by equations developed over a century ago.
I know, it's incredible, isn't it?
It is.
And Stokes' impact extends even further.
Okay.
Remember our discussion about pullback in the Stokes theorem section?
I remember that discussion.
You do.
Yeah, pullback was described as a bridge between calculus and geometry,
That's right.
allowing us to study complex shapes by relating them to simpler ones.
It is.
It was a fascinating concept,
Yeah,
but I admit I had trouble grasping its practical applications.
that's understandable.
Yeah.
It can be difficult to see the connection between abstract mathematics and the physical world,
Right.
but that's precisely what makes Stokes' work so remarkable.
Okay.
Stokes' theorem, a fundamental result in vector calculus, embodies this idea of pullback.
So how does this pullback idea actually play out in the real world?
Well, Stokes' theorem has applications in fields ranging from electromagnetism to fluid dynamics.
Okay. For example, it can help us understand how fluids flow through complex networks of pipes or how electric currents generate magnetic fields.
Okay, I'm starting to see how this seemingly abstract concept can have real-world relevance.
Exactly.
Yeah.
And it all goes back to Stokes' ability to connect seemingly disparate fields through the language of mathematics.
This is all really fascinating.
It is.
We've covered a lot of ground already, but I feel like we're just scratching the surface of Stokes' contributions.
You're absolutely right.
There's so much more to explore, but hopefully this gives you a sense of the breadth and depth of his work and how it continues to shape our understanding of the world around us.
It really does.
It's incredible how someone who lived so long ago could have such a profound impact on our understanding of the world today.
It really speaks to the timeless nature of scientific inquiry, doesn't it?
Yeah.
These fundamental principles that Stokes uncovered continue to be relevant and applicable in countless ways.
You mentioned earlier that the Navier-Stokes equations are still not fully understood.
What exactly does that mean?
Well,
I mean, we use them all the time in engineering and physics, right?
we do, and that's what makes it so intriguing.
Okay.
We know they work. We see them applied successfully in so many areas. But there are still some deep mathematical questions about them that we haven't been able to answer definitively.
So what kind of questions are we talking about?
Well, one of the biggest challenges is proving the existence and smoothness of solutions to the equations in 3 dimensions.
Okay.
In simpler terms, can we guarantee that there's always a well-behaved solution that describes the fluid flow no matter how complex the situation?
That sounds pretty abstract.
It is.
What are the implications of not having those answers?
That's a great question.
Yeah.
It means there's still a potential for unexpected behavior in fluids that our current mathematical framework might not fully capture.
Okay.
Think about turbulence, for example. It's a phenomenon we experience all the time, but it's still incredibly difficult to predict and model accurately.
So there's still a lot of mystery surrounding these equations, even though we use them all the time.
Exactly, and that's what makes them so exciting to study.
Okay.
They represent a frontier of knowledge, and who knows what breakthroughs are waiting to be made.
It's almost like we have this powerful tool, but we're still learning how to wield it effectively.
That's a great analogy.
Yeah.
And the pursuit of a deeper understanding of the Navier-Stokes equations has driven a lot of innovation in mathematics and computational science.
Uh-huh.
We've developed sophisticated numerical methods and computer simulations to approximate solutions and model fluid behavior with increasing accuracy.
So even though we don't have all the theoretical answers, yet we're still making progress in understanding and predicting fluid flow.
Absolutely. And those advancements have led to breakthroughs in countless fields.
Wow.
Think about the design of airplanes, for example.
Okay.
Engineers use these numerical solutions to simulate airflow over wings, optimizing their shape for efficiency and stability.
And it's not just about airplanes, right? These same techniques are used in weather forecasting, climate modeling, even understanding blood flow in the human body.
You got it.
Wow. The ability to model and predict these complex fluid behaviors has revolutionized our understanding of the world around us.
It's amazing to think that Stokes' contributions are at the heart of all this.
It is his work on simplifying those equations laid the groundwork for many of these advancements.
And it's not just about the Navier-Stokes equations.
Right.
Remember those captivating Stokes waves we talked about earlier?
Oh, yes.
Those classic ocean waves with their pointy crests and rounded troughs?
Right. And Stokes' description of these nonlinear waves went beyond the simpler models of his time.
Okay.
He provided a more accurate and nuanced understanding of how those waves behave in the real world.
Why was that important?
Well, for one thing, it revolutionized our understanding of how waves transport energy across the ocean.
Okay.
His work helped us see that these waves generated by wind far out at sea can travel for miles, carrying energy with them, before finally releasing it as they break on distant shores. That's fascinating. So the energy from the wind is transferred to the water, creating these waves that act like energy carriers across vast distances.
Exactly. And as those waves approach the shore, they undergo transformations, changing their shape and height as they interact with the seabed and the coastline.
Okay.
Stokes' theory helped us understand these transformations, which is crucial for coastal engineering.
I can see how that would be important for designing coastal structures and understanding erosion patterns.
Absolutely. And his work has had a huge impact on ship design as well.
Oh, wow.
Understanding how waves interact with a ship's hull is critical for ensuring its stability and safety.
Right.
Stokes' theory provided the tools to model and predict these interactions, leading to safer and more efficient ship designs.
It's incredible to think that equations developed over a century ago can still be so relevant to modern engineering and design.
It truly is. Stokes' work on waves wasn't just theoretical. It had a tangible impact on how we interact with the ocean.
So we've talked about the Navier-Stokes equations and Stokes waves, but what about Stokes' theorem?
Yes.
You mentioned it earlier as a bridge between calculus and geometry.
Ah, yes, Stokes' theorem.
Yeah.
It's a cornerstone of vector calculus and has applications far beyond fluid dynamics.
But what does it actually do? How does it connect calculus and geometry?
Well, in essence, it relates a surface integral over a closed surface to a line integral around the boundary of that surface.
Okay.
It's like saying that what happens on the boundary of a shape can tell us something about what's happening inside the shape.
Okay. I can kind of picture that.
Yeah.
But what are the practical implications then?
Well, it provides a powerful tool for analyzing complex systems.
Okay.
In electromagnetism, for instance. Stokes' theorem relates the circulation of a magnetic field around a loop to the current passing through the surface enclosed by that loop.
So it helps us understand how electricity and magnetism are interconnected.
Precisely. And in fluid dynamics, it can be used to analyze the flow of fluids around objects or through complex channels.
So while it might seem abstract at first glance, Stokes' theorem has very real applications in various fields.
Absolutely. It's a beautiful example of how mathematical concepts can bridge seemingly disparate areas of science and engineering.
It's fascinating how Stokes' work seems to weave through so many different scientific disciplines.
It really is.
From fluid dynamics to waves to these intricate connections between calculus and geometry. It's clear his impact was immense.
Remarkable.
And we haven't even touched on his contributions to optics yet.
Oh, that's right.
Stokes was deeply fascinated by light and its interaction with matter.
Yes, he was.
Oh, right. I'd forgotten about that.
Right.
Tell me more about Stokes' work in the realm of light.
Well, one of his most notable discoveries is his explanation of fluorescence.
Okay.
You know that phenomenon where a material absorbs light of one color and then emits light of a different color?
Yeah, I remember learning about that in school.
Right.
But I don't think I ever understood how it actually worked.
Well, Stokes figured it out. He observed that the emitted light, the fluorescence, always had a longer wavelength than the absorbed light.
Uh-huh.
This observation, now known as Stokes' law of fluorescence, revolutionized our understanding of the energy transitions happening within molecules.
So he essentially cracked the code of why some materials glow in a different color when you shine light on them.
Exactly. And his work laid the foundation for the development of incredibly useful tools like fluorescent microscopy,
Okay.
which allows us to visualize tiny structures and processes in living cells.
Wow, that's incredible.
Yeah.
It's amazing to think how something we might take for granted today, like those glow-in-the-dark stickers we had as kids, has its roots in these fundamental discoveries about light.
It really highlights the ripple effect of scientific discovery, doesn't it?
Yeah, it does.
And Stokes didn't stop there.
Oh, really?
He also made major contributions to our understanding of the polarization of light.
Now remind me what polarization is again.
It's essentially about the direction in which a light wave oscillates. You can think of it as light vibrating in a specific plane as it travels.
Okay, I think I remember that now.
Yeah.
So what did Stokes discover about polarized light?
He developed a set of parameters now known as the Stokes parameters that fully describe the polarization state of light. These parameters are still used today in a wide range of fields, from astronomy to remote sensing.
So these parameters allow us to analyze and understand polarized light in more detail.
Precisely.
Okay.
In astronomy, for instance, they're used to study the light emitted by stars and other celestial objects, revealing information about their magnetic fields, temperatures, and even their compositions.
It's almost like we're deciphering a secret code hidden within the light that reaches us from across the vast expanse of space.
That's a great way to put it.
Yeah.
And in remote sensing, these parameters help us analyze the light reflected from the Earth's surface, giving us valuable information about things like vegetation land cover and even the presence of pollutants in the atmosphere.
So Stokes' work on light has implications not just for understanding the universe, but also for managing our own planet.
Exactly. His contributions touch on fields as diverse as astronomy, biology, and environmental science.
As we wrap up our deep dive into the life and work of Sir George Gabriel Stokes,
Yeah.
I'm struck by the sheer breadth and depth of his contributions.
He is amazing, isn't he?
He truly left his mark on so many areas of science.
He did, from fluid dynamics to waves to light.
Yeah.
Stokes's work has had a lasting impact on our understanding of the world around us. His legacy is a testament to the power of scientific curiosity, the elegance of mathematical thinking, and the interconnectedness of the natural world.
Well said.
Thank you.
It's been an incredible journey exploring the world of Sir George Stokes.
It has.
And I hope our listeners are inspired to keep learning and exploring as well.
Absolutely. There's always more to discover, more to understand.
So true.
Until next time, keep those curious minds engaged.
We'll see you then.